Hello learners, and welcome back to the third video of the battery production series. Today we're going to talk about the battery cell finalization, which is the final step of our battery cell production. And I think a very interesting step also, as it's very different to the previous steps. It's a lot happening inside of the cell here. And yeah, stay curious, stay tuned. We will dive into it and tell you a little bit more in detail about it. It's mainly compiled of the formation and aging, also called maturation process, the degassing, and an end-of-line testing. So this is where the cells get really their final charge from where they are formed and created the SEI structure. I will explain what is an SEI in detail during the seminar. And they are tested for quality and ultimately also prepared for shipment or for the installation in the module and pack for the vehicle use. It's very often said that the formation is really more taking time than the previous production steps, and we will explain you why that is and why the cell spends around 80 to 90% of its time in production in these processes. So stay tuned and let's get started. Welcome back. So we are in the third process step of the battery cell production. After the fabrication of the electrodes and the assembly of the battery cell, we have seen in the previous two videos. Today we're going to speak about mainly the cell finishing, with is compiled out of basically the formation and aging and testing processes. We will explain you what means formation, how it's typically done, how the equipment looks like, what is an aging process, and why it's so important for a good battery cell. First, I would like to define what is the formation. The formation is basically the first charging and sometimes also a few charge-discharge cycles of the cell. And during this process, typically during this process, a lot of electrochemical reactions occur inside of the battery cell, which weren't possible before. So mainly it's forming the solid electrolyte interface, the SEI I already mentioned, on the anode side. And without that formation, basically the battery cell would not work, and it would not really work in a proper way and could not long be used or live in a long lifetime. Hence, this is a super important process of the battery production. It's completely different than the first two major assets. Here we are really talking about electrical activation and then a lot of electrochemical processes inside of the battery cell. And then after the formation, there's the aging process. And doing that, cells are often stored in a certain period of time under controlled conditions, controlled temperature, controlled environment. And like this, we want to stabilize the cell and the chemistry inside of it, and also have quality checks and make sure the cells are really very good, and processes like self-discharge are not happening in a bad way. So it's like basically a curing for the battery cells. I always compare it to a good wine, which also gets better over time and it needs some kind of aging. Also, for some cell formats and chemistries, we need a degassing process. That means we often during the formation and aging have gas forming inside of the cell, and we don't want to leave that gas inside of the battery cell. So degassing removes those gases to avoid any swelling and ensure a long-term stability of the battery cell. And that's done after the formation but before final sealing. And typically each cell then in the last process step gets tested for example, capacity, internal resistance, and other measures, and then they are graded by their performance as well. And only cells that pass all criteria are finally shipped and delivered to the final customer or to the module production, for example. So there are different qualities also coming out of the battery cell. And you might wonder why this is now important, why that is an important process step here to consider. Basically, here we define the cell's performance, lifetime, and capacity is measured here. Early lifetime failures, infant mortality, you call it, are sorted out, and the cell gets its final identity. It's sorted basically, and the barcode is then giving it a traceability from the customer side. So almost 90% of the time the cell spends in production is actually in this stage. So we're going to look into that in detail and see why that's the case and why it takes so much time to charge and discharge and also age the batteries. So if you want to produce, let's say, 1 million battery cells a year, you need to have a lot of space and equipment to have those cells basically at the same time in process, doing the formation and aging. So that normally requires big storage areas and also controlled environment to control the battery cells. So we will talk about that, the high building impacts of the formation and aging process in a bit. So that's it. Yeah? So after that, the cell is ready and can then be transferred to the either final use, or it's brought to the battery module production and assembly, and then out of the modules, battery packs can be produced. This is explained by my colleague Dr. Rueda in another video how that's happening. So after today's video, you will have seen all important processes about battery cell production, how they are connected, what is important, what are typical characteristics, and you will understand why that's such a complex and interesting industry growing worldwide. So let's dive into it. Let's take a deeper look into the single process steps and its alternatives. Before explaining that slide in detail, I would like to give you a little bit insights what's happening in the formation. So during the first charge of lithium-ion battery cells, several critical reactions typically occur. So at the anode side, assuming that's a graphite anode cell, lithium ions intercalate into the graphite for the first time. And that's important. The electrolyte decomposes the anode surface ultimately from the SEI, the solid electrolyte interface. So this is a passivation layer which is reacting and created at the anode side. And at the cathode, there are also some side reactions like surface film formation, but less so than on the anode side. Essentially, the formation activates the battery. Yeah, so you can really see it as an activation of the battery cell and make it ready to be used. But it also consumes a little bit of the lithium and the electrolyte in the process. And typically you have different formation protocols. So this slide here typically lists different typical formation parameters you normally see in production. So typically the formation involves charging at a low C rate, like 0.1, 0.2 C, about to 100% of the SOC, and then maybe a small discharge and another charge at a higher rate. And then typically we see 2 to 3 full cycles gradually increasing the charge rate, or different in the voltage limits, for example. That's you can see here, and there's a combination then also, for example, of different high temperature formation, long-term aging, degassing, and how you run your cell through the cycle is a well-kept secret by most of the battery cell suppliers. So each one has its own formula, its own magic to basically activate the cell, and also how to really put it through aging. So that's very important to consider, and you can see here a few variants and how they are all interconnected. I will let you read the slide for a second and then come back with a little bit more information. So what is the solid electrolyte interface, the SEI, we see in a cell, typically in the formation process? The SEI is a nanometer thick layer that forms on the anode surface during the first charging. The slide shows a schematic overview of an SEI, and it's essentially the result of an electrolyte reaction with the anode, typical graphite, at a low voltage rate, so around 0.1, 0.2 voltage. This reaction consumes some of the electrolyte and the lithium initially, but forms a layer that thereafter protects the anode from continuous electrolyte decomposition, as you see here. Why this is important? The graphite intercalates lithium at about 0 volt, which is so low that it will also cause the electrolyte to break down. Instead of completely ruining the electrolyte, a fortunate thing happens. This layer is created of a decomposition product that coats the graphite, insulating it from more electrolyte, so the reaction stops at some point. But the layer still conducts the lithium ions, so the battery still can work. And this is the SAI layer. So it's basically a protected filmed analogous to a rust on iron, for example, but in this case it's a good rust. It's something we want, and that actually stops further corrosion of the deeper layers of the anode and still allows the lithium ions to go through. So you see here that different cathode materials also have different reactions in the end with the electrolyte, depending on which electrolyte you use, and then the formula of the anode. So basically you can say that that it basically contains lithium salts, organics like lithium fluoride, which comes from the lithium PF reacting, and then, for example, lithium carbonates, L-oxide from the solvent breaking down. And the exact composition is very complex and non-uniform depending on the combinations of material used. For the thickness, it might be around 50 to 100 nanometers, so very small. And yeah, once again, the SEI is essential for a long battery life. A bad or unstable SEI, which is, for example, too resistive, means the cell will keep consuming the electrolyte itself and ultimately lead to a loss of lithium, and with that a capacity loss, and that increases the internal resistance as well. So there's a lot of research going into efforts how to tweak the formation protocols, how to optimize the electrolyte additives to create an ultimate SEI layer in this process. So there is tons of research being done and published. If you are interested in that, please take a deeper look. For the production, I think it's just important to understand what is the SEI and how it's formed, to understand what we need to do with our process equipment and during that time. And here you can see the different chemistries in the SEI layer and different formation protocols, for example, and what is happening then on the anode side of the battery cell. It's important that the forming of the SEI uses up some of the lithium. So typically a few percent of lithium from the cathode is sacrificed to form that SEI, and the lithium ends up in the SEI compounds. This is why its initial efficiency of a fresh cell, first charge versus the discharge capacity, is normally less than 100%. Some manufacturers sometimes compensate that by preloading extra lithium in the cathode to account for this loss. So this is a first cycle loss. And these details show how the SEI even factors into cell design, ensuring the rated capacity and accounts for that loss which will happen. So as an analogy, the SEI is like a seasoning on a cast iron pan. Yeah? So if you cook and you have these old pans, you normally shouldn't wash them, but rather use this kind of old cast to just have a better cooking result. So the first time you use this cast iron, you season it by forming a protective oil layer that then prevents food from sticking in the pan and from rusting. And similarly, the first charge seasons the battery by forming the SEI so that can further use it stable and is stable and doesn't decompose the electrolyte. So I think that's a good analogy to understand what is the SEI layer and how it's formed. An interesting fact, in the 1970s and 80s, a lot of batteries were built until the SEI was discovered. It was a big breakthrough. So researchers found that specific electrolytes would form a stable SEI on the anode side, which allows then a rechargeable cycling. And without it, a lot of early lithium metal batteries kept falling apart because they had not this SEI layer and could allow only for a few cycles reacting until everything was consumed ultimately. So this is, I think, a good example how a controlled imperfection, so this layer, actually makes things better. Coming back to the production, this slide shows a lot of different typical processes happening in the finishing of the cell during the formation, aging, and testing process. So you see processes like the aging, you see the degassing, but also pre-charging, for example, the grading of the battery cells, the final testing. Yeah, so you see all those different building blocks. Not necessarily all have to take place and have to take place in that order. But for simplification, we will today just focus on the following areas. We will talk about roll plasting, why this is important. We will talk about aging, about degassing and sealing, about the formation process, about the end-of-line testing and grading of the battery cell, and the last inspection and folding for some of the cells. So I think this helps you to understand the processes. There is a lot of details which is then specific to the cell format, to the cell chemistry, to the manufacturer itself, to the equipment you use. In general, I think it's important to understand the principles, the production technologies behind it, and the importance of automation and a controlled environment here. And that's where we're going to make a deep dive today, as the parameters basically vary a lot depending on the manufacturer and have a high impact ultimately, but we cannot give the details here for all the different cells. So in some cases, especially the pouch cells have a precondition formation, things like the roll plasting, for example, that is mainly focusing on pouch cells. And we're going to dive that a little bit into detail here in today's lecture. Thank you very much. Before now diving into the details of the production, I would like to explain a bit more about the goods carrier and the storage concept of a chamber concept and why this is important for the formation and aging specifically. So typically cells are transported in a product carrier and the cell contacting takes place inside or outside the carrier. It depends on the concept here. These cells are stored in closed chambers where also you can suppress fire or you have a controlled environment not to contaminate in case of a potential fire or hazard the whole production. So you can have certain areas catch a fire and then suppress it from burning to other regions of your production. This allows also for a shelf concept ultimately, and this allows a high utilization of your space available. And it also allows for a very complex transport and handling system and can offer high automation rate. Basically, both systems in an industry production are normally fully automated. And yeah, especially the storage system is important here. Typically, you see it in a cell production. You have very high towers at the end of the building where those storage racks are stored and where the formation and aging takes place. This is one, due to the storage concept, but two, also due to the long time the cells spend in the formation and aging. We said already at the beginning that they might be there for hours or even days, depending on the protocols. So of course you have to have a storage facility which allows to store them for a longer time. So this is typically a big tower here and of course, due to this heavy load and a lot of cells, the safety requirements are very high in the formation and aging. So indeed, a fresh cell can have defects due to agglomerates, for example, in the coating, or particles which came into the cell, or just manufacturing issues you created during the processes. as it's very complex and you saw that there are many ways for potential errors during the production. So if an internal short, for example, exists, it might fail on the first charge or it might catch fire. So the formation is done and the formation cabinets that have fire suppression or vents for degassing allow that cells can burn, and that happens in a controlled environments. So cells might be inside of metal trays, or the operators need to open it very carefully and normally monitor the production only remotely. So of course, before going to the formation, you want to make sure that you also pre-sort any defective cells, not to have that risk. To increase safety, cells are inspected and removed before the formation processes. And of course, depending on the cell format, it's important to also see that the cell fixtures and carriers are designed specifically for the use case and cell design. Sometimes during the formation, we see that pouch cells, for example, are kept under mechanical pressure, like in a press or constrained by plates, to ensure that they don't swell too much and to help to create a uniformed SEI. Also, depending on where you are in your process, pouch cells might be pressured more or less to have certain effects during the formation and aging. So pouch cells are often stacked between plates during the formation and to mimic the pressure in a battery pack, for example. So ultimately, the SEI is improved by pressure for the pouch cells, and that needs to be considered in the carriers, of course. So to charge all these batteries, you need big battery charger systems with many channels, and normally each cell is connected to an own channel. Sometimes you connect a pair of cells that channels can control then the current, the voltage very precisely, and the formation system might have up to 1,000 channels in a warehouse in a formation room. So each channel can log the data, the voltage curve, the current, and so on. And it's like really like a huge charging farm, you can imagine it. So think of the formation like braking the new engine very gently. Yeah, so you don't go directly to the red line. So you start slowly driving it in, and similarly, we want to charge the battery cells gently from the beginning to create those stable inside layers. It's basically you create that layer on your pen. On the other hand, you have the contrary requirement that, of course, the more time you have your cells spent in the formation and aging, the more money it costs and the more capital it binds. So it takes up to 24 to 48 hours for different cells. And of course, if you create 10,000 of cells per day, you need to have a high capacity, expensive equipment, and of course, you bind a lot of capital here as well during the formation time. So this is why the formation is often cited as the bottleneck and as a very capital intensive process in the production. Ultimately, I want to highlight one more time that the safety during those processes is ultimately very important. And imagine charging millions of cells, and just statistically, one cell might have an internal flaw, and it could easily overheat or vent and start burning. So factories have to plan for that, have to be ready for that. Needs to be fire measures in place, needs to be well ventilated to consider for the exhaust and electrolyte gases coming out of the burning cell. And this is why normally you see the formation also happening in a separate room in those towers with additional safety measures to avoid any big damage. But let's dive now a little bit deeper into the production topics itself. We will start with a process called roll pressing. And I've mentioned it already in the previous video that especially after electrolyte filling, you want to make sure that the electrolyte is really wetting the both separator but also the porous anode cathodes really well, and that you have a homologous electrolyte distribution inside of your cell. You can additionally help that wetting by a process so-called roll pressing. So the cell is typically clamped into a goods carrier, and then you have different rollers pressing on the cell, really massaging the cell. I think I mentioned it in the previous video already. That can either happen right after electrolyte filling or here previously to the formation process. So the roll pressing ensures a maximum of capacity of the cell is achieved by really making sure the electrolyte is evenly distributed. Ultimately, you want to increase the wetting process here significantly. Depending on the manufacturer, sometimes you use also vibrating tables to even support that more. So the creativity, I think, here is limitless. Everything to just create a better wetting and a better electrolyte distribution as a baseline for a good formation of the SEI in the formation process. Just to give you an idea how a typical roll pressing looks like, this is a picture of an equipment here. You see that process parameters are, for example, the contact pressure, the pressure distribution, the geometry of the rolls, or ultimately also the cleanliness and temperature while doing that process. Yeah, I think we have mentioned it enough. Let's dive into the more important processes of the formation and aging in detail and look how that works. Here you can see a sketch of the process of the formation. So first we have an automated transfer of the good carriers into the shelf or chamber system. I explained that before. And sometimes if necessary also with an additional pressure applied. Then we automatically contact the cells, each cell individually, sometimes a pair of two connected to a separate channel of the big battery charger. And then we see through that charger a pre-charging process of the lithium-ion cells to create those SEI as mentioned. That all happens in a very controlled environment and following different formation procedures, which are typically for each manufacturer and cell chemistry and dependent on that. So we want to have a constant control of all the parameters, doing that in a very controlled environment with set temperatures, pressure, and humidity as well. So ultimately, the technologies, alternatives can be just having chambers or a big shelf system. We see sometimes that the temperatures are controlled specifically. Sometimes we use rather high current, rather low current. So sometimes we pressure the cells additionally during the formation. So there's a lot of creativity happening, and normally those specific formation procedures and protocols of the charge-discharge cycles in the formation protocol are kept very secret by the battery manufacturers itself. As you have seen previously, the schematic view of the process and the explanation what is happening in a formation process and equipment, I just wanted to give you a few examples how it could look like in an industry. And you see the sheer scale and size of those equipments, and that it's basically fully automated warehouse with a controlled environment, a lot of channels as you see here. And yeah, this is what is typically happening in the automotive industry. So you want to have a fully automated process here in a separate location and room. So to make sure you are really focusing on getting the cells out and through that process easily, quickly, and with as little hazards as possible. So also avoiding any potential fires or suppressing them at least quickly, so to not risk your whole production here. Next general process step in a battery production could be here the degassing process. That's not necessarily happening for all the battery formats, cells, and chemistries, but especially here in this example for the pouch cells, I would like to explain you why this is important. So why gas is generated, you would ask in the first place. And I think that's easy to understand that during the formation, especially in the first charge, those electrolyte decomposition and reaction in the end produces also gas. So those gases sometimes include CO2 from the breakdown of the solvent, but also H2 and CO, maybe some methane or ethane, depending on the chemistry you use. So in a graphite carbonate system, the CO2 is the prevalent chemistry here and the gas which is created, and we want to get that out of the battery cell, of course. So ultimately those gases collect inside of the battery cell. And in this example here, in the pouch cell, you will see that the pouch has a swelling effect. And sometimes you leave gas in a special area, you leave additional material to have that gas pocket. I mentioned that in the second video, and here it's where it comes in place. So if the gas is left inside, that would create an increase of the cell impedance because the gas is collected in the pores and pushes out the electrolytes, for example, and that causes long-term swelling and increase of the swelling. So degassing, especially for pouch cells, is enforced here. So for pouch cells, degassing is typically done by slicing a corner of the pouch open if there's no special valves, or by using a built-in degassing valve. It depends on the geometry here, but also sometimes you leave a certain gas bag, which you then press the gas in and close the seal again, and can cut the separate gas bag and dispose it accordingly. Likely they put the pouch cell in controlled environments, for example, a vacuum chamber, and puncture then the gas bag here carefully to let the gas out under the vacuum, and it's extracted correctly. And then you can also seal the pouch cell here, again with a similar principle as I explained in the second video. And of course, you might wonder why we can't design an electrolyte or a combination of electrolyte and anode material that doesn't create any gas. So there's of course research going into that direction to have an SEI which forms then less or no gas by using different additives. But ultimately, some gas is almost inevitable to be created with the current chemistries. So degassing is an almost standard step, and of course that adds a lot of complexity into the handling of the cells if you need to open or degas all the or each single cell, and handling the gas which is created there, making sure there's also no water coming in the battery cell again. So that is creating a lot of complexity here. And looking at now the degassing of the prismatic cell, typically you have a valve for doing that, and the cell is then opened or degassed through the hole which is there, and then only finally sealed, for example, with a laser welding. So you really leave a dedicated space to degas the battery cell here. Sometimes you have also a second filling of electrolyte and additives which can be added then to increase battery performance. Again, we can only present you here a very schematic overview about the processes, but each manufacturer there uses his own combination of processes, and the order of processes might differ here as well. So you see here our equipment actually for degassing we use at the Aachen University, and that is on a research level, not on an industrial scale, but basically it applies vacuum to the pouch cell, applies an external pressure, and then seals off the extra gas casket of the pouch cell. And especially looking at pouch cells, we sometimes see an additional step which is called the inspection and folding, where you take an additional optical check for any defects in the pouch bag of the cell, and you sort out cells which might have errors. Also, you very often fold and, if necessary, glue additional edges to reduce just the external dimensions of the battery cell. So you want to make it as compact as possible, and that can help to just fold the extra amount of pouch foil here, for example, on the sides, or you fold the contactors in a certain dimension or position that you can use them in the next process. Of course, ultimate goal is to reduce the minimum or the maximum volume, but also to stabilize and reinforce the seal of the pouch bag, but also make sure you have the correct geometry of the battery cell for next processes which is used in, or the tabs are bended in the correct direction. So this happens especially for pouch cells very often. Coming now to another major important step of the cell finishing, the aging. And yeah, first of all, what is aging? In this context here, it means storing the cells for a period of time after the formation and let them stabilize, so make sure they can catch or we can catch any of potential failures. And we typically see different types of aging, for example, high temperature aging, normal temperature aging, low temperature aging, and the combination of all those different temperature ranges and procedures can take up to even 3 weeks. So it's like a stress test and conditioning period for our new produced cells. So first, we want to make sure that also in that process we have a maturation which serves certain quality assurance. So we want to regularly measure each cell's open circuit voltage, the OCV, while in the storage. And if an OCV drops faster than a specific rate, it would indicate a certain self-discharge or an internal leakage or problem that the cell might be defected and should be scrapped. So that's often called voltage monitoring for potential failure detection. Then in the high temperature aging, we would first store the cells at a higher temperature, for example, around 40, 50 degrees for some days, because the heat might accelerate certain side reactions and electrolyte wetting of any remaining dry pores inside of the battery cell. So also it would help the electrolyte penetration and speed up the initial degradation that might happen, effectively burning in the cell. And higher temperature accelerates the diffusion of the electrolytes just more. That typically might take a few days to a week, around 45 degrees temperature. In normal temperature aging, you either in a combination of high temperature phases, the cells are stored at a normal room temperature, around 20 to 25 degrees, for a certain amount of time, and that allows the cells to cool down, continue to observe them in certain conditions, and monitor also here the measures. So especially a combination of high temperature, normal temperature aging is standard, and the cells undergo that procedure again very dependent on the chemistry and on the manufacturer, on the cell size also. Typically, the cells are here stored in high shelves or high warehouses, and we see pictures of cells with thousands of cells in a rack, and each cell needs to be more monitored frequently, but it's not monitored full time. So sometimes we have an automated storage system where robots can connect the cells over time, and then make sure that also the right processes are happening inside of the cell, and we're also taking out any failure out of the cells. Of course, that's a logistical challenge as well, but typical automation problem. Also, we want to have again an environment which is controlled, constant temperature which is needed, of course, but also other safety requirements like potential fire suppressions, and making sure it doesn't catch fire off the whole shelf, and having ways to dispose failure cells and avoid any ignition or venting of the cells. And the system should be able to handle it. Also, you want to consider the density of the packaging. to have on one side the cells stored efficiently, but also on the other side contain any potential incidents. So once again, here aging can take up to a few days and weeks. So of course here again you have huge warehouses and capacity you need to connect, and also a lot of equipment to monitor the cells. So this is typically a very long capital intensive and also working capital intensive process. You also want to make sure that the cells in the end of the process reach a certain state of charge, SOC, and also you store them at a certain state of charge during the aging. So, for example, you could do it at around 80% for the aging process, but then have the capacity around 50% for shipping. So, it depends here again on what your customers ask for, but also what your chemistry likes the most for the process. Either way, the state of charge is monitored and is an important factor here as well. Also, the OCV, as I mentioned, is important to monitor over time, and also monitor if it drops more than the normal drop we see in any cell over time. So why aging matters? Because aging catches problems like self-discharge, shortages, gas generation that weren't possible to detect immediately, and it's essential also like to make it soak and let all the reaction happen and settle down. Ultimately, for example, the electrolyte needs to soak in fully, minor reactions need to be completed, and yeah, after the aging, the cell is just more stable. Also, from a production standpoint, storing the cost of storing the cell is important and costly, and it ties up to inventory. You see an example picture here of the big storage racks you need. And yeah, ultimately, it's just still much more safer than having no aging or moving the aging, for example, to shipping. When a cell burns in a container, of course, that has a much higher impact than if you can sort out a cell here during that days and weeks into the aging process. So just manufacturers in the end bite the bullet, if you want to say, and hold the cell to ensure only stable cells in the end are shipped. And yeah, if anyone finds a way to really reliably predict the quality after the aging, of course you could reduce that time and could save a lot of money. And that is definitely a room to innovate and make sure there is a shorter aging process and a more stable prediction on cell quality. Typically, before then shipping the cells, we also have an end-of-line testing, and that's the final check to make sure each cell meets specification before it leaves the factory. So it's like a quality control where each cell gets a small report, is connected to the identification code of the cells, and they're also typically graded into different tiers based on their capacity performance, and so they are matched in the grading and shipped accordingly and according to the customer's perspective. So you see here a typical process sketch of a end-of-line testing and grading station. All cells are brought to a certain level of state of charge, the SOC. They are measured for example, depending on the manufacturer, of course, a pulse test, internal resistance, optical inspections, the OCV, the open current voltage, leakage tests, and further tests can be carried out. Also, a lot of optical pictures, for example, can be taken here. Then they are sorted and graded according to their performance, and once they have been tested, they pass successful, they get packed and can be shipped. Looking now a little bit more in detail, what is in the end checked? For example, the capacity check. They, for example, can discharge the cell if it's not already at the shipping voltage to measure the capacity and predict the capacity. Sometimes they charge even to full and then discharge to a standard level to see how many ampere hours or milliampere hours it delivers. Many times the aging already had them fully characterized, so they might simply discharge to a shipping state of 30% SOC, for example, but in the end, measures are around 30% of the voltage to 60-70% of the voltage before shipping, depending on how the customer wants it and how long the batteries are or will be also stored. Then typical tests for the internal resistance, they could do, for example, a DC IR test by applying a short pulse of a current, measuring the voltage drop, or an AC impedance test. So there are different opportunities to test the internal resistance. A pulse test can also yield the DC resistance, AC tests in the end yield the impedance value. And of course, this is crucial for the power performance grading of the cells in the end. Sometimes you also measure the self-discharge or the OCV loss. If the aging was really short, they might measure the OCV specifically one more time after some additional time for detecting self-discharge. And typically, you do that already during the OCV checks of the aging, and they typically want to repeat that during the final tests. Sometimes you do specific leak testing, specifically for PowerShell prismatics checks, where they also make sure the cell is really airtight, there are no micro leaks or electrolyte or air ingresses of the cell. You do that sometimes by a helium leak test, if cells were exposed to helium in aging. And yeah, there are different ways to test a leak of the cells, and you want to make sure that no untied cell leaves the production here. For some examples, they also will weigh the battery cell to ensure that the electrolyte is still the same as in the beginning of the process, so the mass should be ultimately the same, minus, of course, the gas you released during the degassing. A lot of mechanical inspections can happen, ensure there is no swelling of the dimensions, the battery cells are in spec, there's no damage of the terminals, and the thickness of the pouch cells, for example, is still correct, and you can ensure that there is no swelling happening above the specification you defined. And also you want to make sure the sealings, for example, of the pouch cell still look good and the foil is not impacted. Typically, there's then a grading happening. They classify the cells into different classes, for example, 3 or 10 classes. A grade A cell might be 100 to 105% of the nominal capacity and a low resistance, a grade B cell around 95 to 100%, and a capacity at specification or slightly higher. And this allows ultimately matching the cells in the pack and modules you want to create, so to have a much better balanced module and battery to use in later cases. And of course, lower grade cells might be also sold for less demanding applications, for smaller price and for smaller batteries. Yeah, I think there are many ways to test. You saw some. What is important is also the traceability of the cells, that you can really understand which production processes the battery has seen, which batch of the mixing, for example, of the anode cathode they are from. So the traceability is recorded also and often tied to the cell's serial number or barcode. So the manufacturer has a record of each cell's performance, and that can be, of course, useful if there's any analysis needed after field returns or later in the process. So if someone claims the cell was bad when the battery produced. After grading, sorting, and testing, the cells are packed, and yeah, they normally use different trays, for example, from plastic, and boxes for transport. Sometimes they also specifically insulate the terminals with a cap or with a cover or with a glue, and the crates, and then transport them under normally the UN regulation for transporting batteries. You can take a deeper look if you're interested into that. Yeah, so at this point, our cells are finished, tested, and graded. They have a barcode, their tester is recorded, and they're ready to be shipped to a customer, for example, an EV battery manufacturer, and they will receive those cells and sometimes often even do some own incoming inspections, especially after the shipping was long, and at least doing some sample tests to make sure the batch is correct. So that was the battery production in general. Now the cells are ready, tested, and ready to be used. I think we can assume that they have seen a lot, and they are ready to be used and further built into a product. This is going to be explained in a different video, but I like to highlight that if battery production were established in different regions of the world, I think it's always important to have a good quality and system in place, setting up facilities which require a lot of expertise, and you have seen a lot of investment and also, of course, a lot of time, and capital and a lot of energy, and you want to make sure that this is a thoughtful adventure and you have everything in place to justify such an investment and step. I will summarize a few more topics here at the end of this lecture, but for the production we have seen now all important steps. As we have spoken about safety and importance of it, some more insights here to the pouch cell, for example, especially for cells with high energy density, it might make sense to have integrated safety elements in a pouch cell to decrease the risk of potential failures. And that you see here on the slide, the for example, electrical connection between the cell and stack and the cell terminal might be interrupted by the expansion of force of an inflated cell if we have a swelling due to gas formation, and that could basically prevent potential degassing or burns of the cell by just deconnecting the electrical connection. And this can be irreversibly interrupted by the expansion of the pouch film, as you see here in this example. Similar measures we can also see for our round and cylindrical cells, for example with the CID, the current interrupt device, and with an internal pressure the cell is exceeded and the CID would disconnect the connection between the cathode and the contact. That would lead to an irreversible separation of the connection and close the circuit basically. So the CID can be activated by an overcharging, overheating, internal short circuit, or a significant overcharging of the whole cell. We might have additionally safety valves or degassing elements. That's basically to really have an internal pressure rise abruptly, then having a determined breaking point to really degas the cells controlled and in a certain direction, not to have the gas coming out uncontrolled. Another option could be positive temperature coefficients, the PTC. So if high currents or temperatures are reaching during a charge-discharge process, the PTC would increase the resistance and like this reversibly reduce the current flow. So as you see, safety is important. It's not just defined by production, but also in production you want to make sure you don't bring any particles. But as safety is important and as we are handling potential fire hazards and safety hazards due to electrolyte, for example, or the gas which is created, we want to make sure we have the right measures also on the product side in place. Some you have seen here. If you now looked at all the production processes, especially for the cell finishing, it shows a floor plan here, a diagram of the different areas. You might get an understanding how that all ties together and how automated that all needs to look like. That would be, I think, interesting to consider how big that factory needs to be and how many different processes you are following here, making sure that everything is in place, everything is happening in a controlled environment, but also potential hazards like degassing or a burning of a cell are considered and not affecting the whole production then. Just to summarize also the different environments we are working in. You see here we mentioned a clean room often, we mentioned a dry room often, we mentioned everything needs to happen in a clean environment. And normally you do separate the three major process steps by this. Yeah, so the first one can happen in a not dry room, can happen in a dry room, but definitely it should be a clean room in a controlled environment. The assembly of the cell definitely should happen in a very dry environment, in a dry room. And then the last step can happen in a controlled environment. And you see the principle of a dry room because we get that asked very often how to make the air dry here. So that's how a dry room would work. And yeah, you can take a better understanding of the principle of a dry room, creating the dry air for the room here. So we are at the end of an exciting journey about the cell production. I think we have started at the raw materials, talking about the different cathode anode materials, the foils, and then we went through the electrode production in video 1 about the mixing, about the coating, the drying, the calendaring, the slitting process before handing it into a vacuum drying and handing it over in our second video to the cell assembly. In the cell assembly, we talked about the first connecting and rolling or stacking the separate electrodes with the separator, the anode cathode separator combination, and then either winding or stacking it, then adding some tabs to connect it also to the outside world, then fitting it into the housing, either the pouch, the prismatic, or the cylindrical housing, then making sure the electrolyte is filled correctly and the right amount, and before then closing the battery cell and making sure everything is corrected. And in this video here, we have talked a lot about the cell finishing. Specifically, we have talked about the formation and aging and the final testing here, and why this is so important and such a long process in production. We have seen different examples for combination of testing and formation protocols, and we saw some pictures and examples from industry. And yeah, I think everything like this has shown it's an enormous journey, requires a lot of engineering, of know-how about chemistry, quality control. Just mixing the slurry is something very different than formating the battery cell. And yeah, that's, I think, the exciting journey we shared here in the last 3 videos. So to just summarize, it's a complex but well-established process with a lot of specialists and equipment builders around the world. Quality is key and consistency is super important to optimize battery safety and quality output. The environment is a very important and crucial point where you need to have your processes happen. And of course, we always have trade-offs between the different optimization variables, like doing it fast or doing it safe. The cost versus quality, of course, is a balance we need to consider here. Just linking it to also different regions in the world, I think we have seen that a lot of raw materials come from, yeah, for example, Africa, African soil, and there's real possibility, in my opinion, to moving some of the value chain, not just the mining, but also the refining, the production of the components, the raw materials, the precursors, for example, but maybe even assembling battery cells into the continent here. Some current countries are already starting pilot projects in Africa. Some companies are very active in setting up production, both for the electrodes, but also, for example, for recycling plants, and want to create a local battery value chain. And I think that's a great thing to hear. And with a growing shift to electric vehicles, to renewable, to more electrification in every sector, I think it's also a necessary step. We need to make sure that the energy is stored there and that we are not shipping batteries around the globe, the material from here to there and back, so that value chains are created locally and also the necessary experience and expertise is built locally. And yes, it requires a lot of investment, a lot of infrastructure and technical know-how, consistent power, high power demands, very clean facilities, and very skilled people. But I think all those challenges can be overcome with the right team on board, with the right partnerships, with the right policies in place. Because 20 years ago, China was not a major battery player, and now it's dominating the world with its equipment, with its also battery manufacturers. And I think we can take a great example here, how that could look like in different regions in the world. So I would like you, all the engineers out there who listened to me in the last 3 hours, advise keep an open eye on the battery technology, stay curious, look at what's happening in the battery sector, and considering, for example, specializing in certain areas like the electrochemistry, the material science, the manufacturing engineering. And I think there's a big opportunity for each one of you. I would love to hear more from you and see a lot of gigafactories being built in Africa and around the globe, obviously, and visit you maybe at one day and go through an active production with you. So thank you for sticking through this deep dive. Thank you for listening to me. In case you have ideas or want to give feedback or have more questions, please reach out, find me on LinkedIn. I think that's the easiest way to do. And just consider every time you use your phone now how much effort goes into the small batteries inside of your phone. And don't take it granted. It's really a difficult and very interesting product, the battery, and there's yet a lot to come and a lot to optimize, and we're just at the very beginning of a huge interesting journey. So thank you very much, and see you all soon.